Welcome to another journey of science to sleep by. Tonight, we're asking one of the deepest and most mysterious questions in all of science and philosophy. Did the Big Bang come from nothing? This isn't just about physics. It's about existence itself, about why there is something other than nothing. So, lay back, let your mind wander, and let's explore the universe together as you drift into sleep. When we begin to talk about the Big Bang, we are not simply recounting a scientific hypothesis. We are diving into the origin story of the universe itself. Imagine for a moment the night sky above you, filled with countless stars, galaxies, and nebulae scattered across the canvas of space. Each point of light represents not just a star, but an entire history of cosmic processes, billions of years in the making. All of this, the vast structures of galaxies, the delicate balance of forces, the very atoms that make up your body, trace their lineage back to a single event, nearly 13.8 billion years ago. That event is what we call the Big Bang. The Big Bang Theory is our best scientific description of how the universe expanded from an unimaginably hot and dense state into the cosmos we observe today. But to understand it, we must step into the mindset of a scientist, one who gazes into the sky not with casual wonder but with precise instruments and equations. The story began in the early 20th century, when astronomers like Edwin Hubble discovered that galaxies were moving away from us, and the farther away they were, the faster they seemed to be receding. This astonishing observation suggested that space itself was stretching, like dough rising with raisins spread through it. It wasn't that galaxies were racing through space. It was that space itself was expanding, carrying galaxies along for the ride. If everything is moving apart, then at some point in the past, everything must have been closer together. If we keep winding the clock backwards, compressing galaxies into smaller and smaller volumes, we eventually reach a moment when all of space and time were concentrated into an incredibly hot, dense state. This, according to modern cosmology, was the beginning of the universe as we know it. But the term Big Bang can be misleading. Many people picture it as an explosion in space, like fireworks bursting outward from a single point. That image, while dramatic, doesn't quite capture the reality. The Big Bang wasn't an explosion in space, it was the expansion of space itself. There was no pre-existing stage where the explosion happened. Space and time themselves began in that event, and everything we call the universe unfolded from it. Imagine a balloon with dots on its surface. As the balloon inflates, the dots move away from each other, not because they're traveling across the balloon, but because the surface itself is stretching. That is a closer analogy to what cosmologists mean when they describe the Big Bang. One of the most remarkable aspects of this theory is how well it fits the evidence we see in the cosmos today. In the 1960s, scientists discovered a faint background glow of microwaves filling the universe in every direction. This radiation, called the cosmic microwave background, is the afterglow of the Big Bang itself, light that has been traveling for nearly 14 billion years, stretched into the microwave part of the spectrum by the expansion of the universe. When we look at this faint signal, we are seeing a direct imprint of the universe when it was only about 380,000 years old, a baby picture of the cosmos. This discovery was so significant that it confirmed the Big Bang model as the leading explanation for our cosmic origins. The Big Bang Theory also explains why the universe contains the mixture of elements that it does. In the first few minutes after the expansion began, conditions were so hot and dense that atomic nuclei could form. Protons and neutrons collided, creating the first elements, mostly hydrogen and helium, with trace amounts of lithium. These light elements became the raw material from which stars and galaxies later formed. The fact that our universe is overwhelmingly composed of hydrogen and helium matches precisely what the Big Bang model predicts. The heavier elements, like carbon, oxygen, and iron, were forged later inside stars and spread through supernova explosions. But the original light elements are direct evidence of those first fiery minutes of cosmic history. When you think of the Big Bang, you may picture the beginning as a tiny speck, infinitely small, infinitely dense. This concept is often referred to as a singularity, a point at which our equations break down. But it is important to realize that the singularity is not necessarily a physical object we can imagine, but rather a placeholder for the limits of our knowledge. General relativity, the theory developed by Albert Einstein to describe the fabric of spacetime, predicts this singularity, but we know that quantum physics must also play a role in those first moments. Unfortunately, we do not yet have a complete theory that unites quantum mechanics with general relativity, and until we do, the true nature of the universe's beginning remains uncertain. Still, the Big Bang theory gives us an extraordinary framework. It describes how the universe has evolved over billions of years, from that searing, dense beginning to the vast and complex cosmos we inhabit today. It helps us understand not only where galaxies and stars come from, but also how time itself has unfolded. Every tick of the clock, every heartbeat, every second of your life, has been carried along by the expansion of the universe that began with the Big Bang. Think of the scale of this. The universe is about 13.8 billion years old, which means that light traveling at 186,000 miles per second has been moving through space for nearly 14 billion years, and still has not crossed the entire cosmos. The observable universe, the part we can see, is about 93 billion light-years across, and it is still expanding. That means the universe is not just old, it is vast beyond comprehension. And yet, despite its immensity, all of it began from something so small and so dense that it challenges the limits of human imagination. The Big Bang also raises profound philosophical questions. If the universe had a beginning, what came before? Was there a before if time itself began with the Big Bang? These are the mysteries that stretch our understanding and remind us that science does not just provide answers, but also opens doors to deeper questions. Even the scientists who developed these ideas were humbled by the enormity of what they uncovered. Georges Lemaitre, a Belgian priest and physicist who first proposed the idea of a primeval atom, saw no conflict between science and wonder. For him, the Big Bang was not just a scientific theory, but a profound insight into the nature of reality. And yet, the Big Bang is not the final word. It is a theory supported by evidence, but it is still a work in progress. Every new telescope, every new measurement of distant galaxies or the cosmic background, refines our understanding. With tools like the James Webb Space Telescope, we are now peering back closer to the dawn of time, seeing galaxies as they formed only a few 100 million years after the Big Bang. Each observation gives us a clearer picture of how structure emerged from that initial state. So, when we talk about the Big Bang, we are not just telling a story of the past, we are participating in an ongoing journey of discovery. It is a journey that unites science, philosophy, and imagination. It is a story that begins with the universe compressed into an almost inconceivable state, and then expanding, evolving, and giving rise to everything we know, the stars, the galaxies, the planets, and even us. It is a story that reminds us how deeply connected we are to the cosmos, because every atom in our bodies was once part of that early universe, forged in the fire of creation that began with the Big Bang. When we hear the word nothing, our everyday intuition paints a simple picture, a complete absence. An empty void, a blank canvas without substance, form, or even possibility. For many, nothing is the absolute negation of being. It is what remains when all matter, all energy, all light, and even all thought have been stripped away. In ordinary language, nothing is a hollow silence, the absence of something, a vacuum devoid of content. Yet, when scientists and philosophers step into this territory, they quickly realize that nothing is not such a simple concept. The closer we look, the more slippery and elusive the idea becomes. It forces us to ask whether nothing can ever truly exist, or whether what we call nothing is just another version of something in disguise. In the context of the universe, this question takes on extraordinary weight. If the Big Bang was the beginning of all things, then did it arise out of absolute nothingness? If so, what does that mean? Was there a moment before when there was truly no space, no time, no energy, no laws, and no possibilities? Or was the so-called nothing pregnant with hidden rules, with quantum potentialities, with a framework from which the universe could emerge? These questions may sound like riddles, but they are at the core of cosmology and philosophy. Science has given us ways to redefine nothingness in ways that may surprise you. Take, for example, the concept of a vacuum. In physics, a vacuum is the absence of matter, an empty region of space where no particles reside. To the human imagination, that sounds like nothing. Yet quantum physics has shown us that even a vacuum is not truly empty. Instead, it is a restless sea of activity, bubbling with what physicists call quantum fluctuations. According to quantum theory, fields exist everywhere in the universe, and even in the absence of particles, these fields can jiggle and fluctuate. Tiny, virtual particles pop into existence, and then vanish almost instantly, borrowing energy from the vacuum in accordance with the strange rules of quantum mechanics. So the empty space between galaxies is not a true nothingness, it is alive with invisible energy and fleeting events. This leads to a profound rethinking of what nothing means. If what we call nothing in physics is still something fields, energy, fluctuations, then can we ever truly get to a state of absolute nothingness? Some physicists argue that such an absolute nothing might not even be possible, because the laws of physics themselves may ensure that there is always something. In this view, the vacuum is the lowest energy state of reality, but it is still not the absence of reality. It is like a calm ocean surface that still holds the potential for waves. The ocean is never truly still, even when it looks that way from afar. Philosophers, however, take the debate in a different direction. To them, nothing is not just the absence of particles or fields, it is the absence of being itself. From this perspective, the scientific nothing is not really nothing at all, because it still assumes that the laws of physics exist, that time and space exist, and that quantum fields exist. A philosopher might ask, where did those laws come from? Why do they exist rather than not exist? Science can describe the conditions within our universe, but whether those conditions themselves required some prior existence is a deeper metaphysical problem. For many, this is where the divide between physics and philosophy becomes most striking. Physicists may be satisfied with saying that the universe could have arisen from quantum fluctuations in a vacuum, because in that sense, nothing gave rise to something, but a philosopher might respond that this is cheating, that what scientists call nothing is really a disguised form of something. After all, a quantum vacuum is governed by rules, probabilities, and structures. If the Big Bang came out of such a vacuum, it did not come from absolute nothingness, but from a realm that already had potential built into it. This tension also reaches into questions of time. If the Big Bang marked the beginning of time itself, then asking what happened before the Big Bang may not even make sense. Time, in that case, did not exist, so there was no before. But then what does it mean to say the universe came from nothing? If there was no time, then perhaps there was no state of nothingness to precede something. The emergence of time and space themselves may be inseparable from the emergence of the universe. The nothing that came before might not even be describable in human language, because all our words rely on concepts like space, time, cause, and effect. Another way to think of nothing comes from mathematics. Some physicists have proposed that the laws of mathematics themselves may be fundamental, existing in some abstract way independent of the physical universe. If this is the case, then perhaps even if there were no space, no matter, and no energy, there would still be mathematics. And from mathematics, rules of physics could emerge. In this strange sense, nothing may still carry the ghost of structure, the shadow of possibility, waiting to be realized in a physical form. We also find hints about nothingness in experiments in particle physics. In laboratories, scientists have created conditions where particles appear to emerge from a vacuum, demonstrating that empty space can generate energy and matter under the right circumstances. These experiments suggest that the universe itself may have sprung from a similar process on a grand scale. But again, the nothing we are talking about here is not truly nothing, but a vacuum structured by the laws of physics. There is also the mystery of dark energy, the strange force that seems to be driving the accelerated expansion of the universe. Some cosmologists think dark energy may be a property of the vacuum itself, another reminder that what looks like emptiness is far from void. If the vacuum itself has energy built into it, then our understanding of nothing becomes even more blurred. The empty spaces between galaxies may be filled with the very energy that shapes the fate of the cosmos. In the end, when we ask whether the Big Bang came from nothing, we are really asking two different questions at once. One is a scientific question: can the universe arise naturally from a quantum vacuum, from fluctuations, from the laws of physics as we know them? The other is a philosophical question: why do those laws exist at all, and why is there something rather than absolutely nothing? The scientific question pushes us toward models of cosmology and quantum theory. The philosophical question pushes us toward the limits of language and thought, where even our definitions of nothing begin to dissolve. For the purpose of science to sleep by, it is enough to recognize how layered and profound this idea of nothingness really is. When you close your eyes and imagine a vast black space, you may think you are picturing nothing, but in reality, what you are picturing is something, a void filled with space, a stage where things might happen, a silence where sound could someday emerge. The true nothing, if it exists, would not even allow that. It would be the absence of absence, a concept that our minds can barely grasp. And yet, out of that mystery, out of that unfathomable silence, the universe may have been born. When physicists speak of quantum fluctuations, they are referring to one of the most counterintuitive and fascinating features of the quantum world: the idea that even in a vacuum, even in a region of space stripped bare of particles, energy, or light, there is never absolute stillness. Instead, reality itself seems to shimmer with uncertainty. Tiny, fleeting disturbances bubble into existence and vanish again, as if the universe cannot help but stir with restless possibilities. To the human mind, trained in classical thinking, this seems absurd. We imagine that emptiness should be calm, that zero means zero, that nothing is nothing. Yet quantum mechanics shows us otherwise. On the smallest scales, governed by probabilities and wave functions, nature refuses to sit still. Even emptiness vibrates with potential. To understand why, we must first recall that in quantum theory, uncertainty is built into the very structure of reality. Heisenberg's uncertainty principle tells us that certain pairs of physical properties, such as position and momentum, cannot both be known with perfect precision. If we pin one down, the other becomes fuzzy. This principle extends even into the vacuum itself. In the quantum picture, fields permeate all of space, and they can never have exactly zero energy, because that would mean knowing both their value and their rate of change with absolute precision. Instead, they jitter and fluctuate. These fluctuations are not particles in the usual sense, but rather virtual particles, ghostly presences that appear and disappear so quickly they cannot be directly observed. Yet their effects are measurable. The most striking thing about quantum fluctuations is that they are not merely theoretical abstractions. We see evidence for them in real experiments. One of the clearest demonstrations is the Casimir effect, where two metal plates placed very close together in a vacuum experience a tiny force pulling them together. This force arises because the quantum fluctuations of the vacuum are slightly different inside the gap between the plates than outside it. The plates move, not because of some hidden spring, but because empty space itself is active. Similarly, quantum fluctuations are responsible for effects like spontaneous emission in atoms and subtle corrections in particle interactions measured in particle accelerators. What this means is that emptiness is never truly empty, is a restless ocean of temporary energy shifts. Now imagine magnifying this idea to the scale of the cosmos. If quantum fluctuations can nudge atoms and particles in a lab, could they also play a role in the birth of entire universes? Some cosmologists believe the answer is yes. According to certain models of quantum cosmology, our universe itself may have originated as a quantum fluctuation in a kind of primordial vacuum. In this scenario, the laws of quantum mechanics do not just allow for particles to pop in and out of existence, but in principle, whole universes as well. The reasoning is that if the total energy of a universe can balance out to zero, where the positive energy of matter and radiation is offset by the negative energy of gravity, then such a universe might arise spontaneously, with no need for a prior cause in the classical sense. From this perspective, the Big Bang could be understood not as an externally triggered event, but as a natural outcome of quantum uncertainty applied on the grandest scale. This idea is supported by the inflationary model of cosmology, which suggests that in the earliest moments of the universe, a tiny quantum fluctuation in a high-energy field could have triggered a rapid, exponential expansion of space. Inflation solves several puzzles in cosmology, such as why the universe appears so uniform on large scales, and why it is so flat. But it also carries within it a deeper suggestion that universes might be able to sprout like bubbles from the quantum foam. In some versions of inflation, this process could even be eternal, with universes budding off endlessly from the underlying quantum substrate, creating what is sometimes called a multiverse. To contemplate this is to stretch the imagination. The idea that our entire universe, with its galaxies, stars, and conscious beings, could have emerged from a microscopic jitter in a quantum field sounds almost magical. Yet it is a serious scientific proposal grounded in the mathematics of quantum theory and general relativity. It forces us to rethink the relationship between nothing and something. For if the vacuum itself is never truly nothing, if it always contains fluctuations and potential, then perhaps the line between nothingness and being is not as sharp as we once thought. Perhaps the leap from nothing to something is not a leap at all, but a natural blossoming of possibility inherent in the quantum fabric of reality. Still, one must pause and ask, what about the rules themselves? Quantum fluctuations occur because the laws of quantum mechanics exist. If the universe emerged from such a fluctuation, then where did the laws come from? Were they always there and into the fabric of reality, even before reality unfolded? Or are the laws themselves emergent, arising with the universe rather than before it? These are questions that stretch beyond current science and border on philosophy. Yet, they remain essential, because they remind us that to say the universe came from a quantum fluctuation is not the end of the inquiry. It is a profound step, but it opens new mysteries about why the rules of the game exist at all. One way to frame the problem is through energy. In everyday experience, we think of creating something as requiring input. If you want to build a house, you need bricks, wood, energy, and effort. Nothing comes from nothing. But in physics, the situation is more subtle. A universe can, in principle, arise with zero net energy, because the positive energy of matter is balanced by the negative energy of gravity. The idea, famously suggested by physicists like Stephen Hawking and Edward Tryon, is that the total cost of a universe might be zero, making its spontaneous birth possible without violating conservation laws. This doesn't mean the process is simple or fully understood, but it hints at a mechanism by which something could arise without a traditional cause, at the same time. Quantum fluctuations also leave imprints that we can study. In the early universe, during inflation, tiny fluctuations in the quantum fields were stretched to cosmic scales. These fluctuations became the seeds of all the structure we see today. The galaxies, clusters, and cosmic web that fill the universe are, in this view, the magnified echoes of microscopic jitters from the dawn of time. When astronomers map the cosmic microwave background, the faint afterglow of the Big Bang, they see tiny variations in temperature, patterns that reflect those primordial fluctuations. In this sense, every galaxy in the night sky is a monument to quantum uncertainty, a reminder that the largest structures in existence were sculpted by the smallest wiggles of reality. This interplay between the microscopic and the cosmic is one of the most beautiful aspects of modern science. It tells us that the laws governing the tiniest particles are inseparably linked to the grandest scales of space and time. It tells us that when we study quantum mechanics, we are not just probing the invisible world of atoms, but but also reaching toward the origins of the universe itself. And it suggests that the birth of our cosmos may not have required a grand external push, but instead could have flowed naturally from the restless energy of the quantum vacuum. Still, there are limits to what we can say. We cannot yet test these ideas fully. The very first instant of the universe, the so-called Planck epoch, where quantum gravity dominated, remains hidden from us, beyond the reach of current experiments. Our theories, elegant as they are, may only be approximations of a deeper truth yet to be uncovered. And so, while quantum fluctuations offer a compelling path to explaining the birth of the universe, they also remind us of how much remains unknown. The boundary between science and speculation is delicate here, and humility is as important as imagination. For a listener drifting into sleep, perhaps the most calming realization is that uncertainty itself may be the root of everything. That the same principle that makes an electron impossible to pin down, that makes particles flicker in and out of existence, may also be the principle that gave rise to the stars and galaxies. That in the very fabric of uncertainty lies the possibility of creation, and that the universe, vast and intricate as it is, might ultimately be the grandest fluctuation of all. To understand the birth of the universe, and to even approach the question of whether it could have come from nothing, we have to grapple with one of the most profound revolutions in human thought, Albert Einstein's theory of general relativity. Before Einstein, space and time were thought to be fixed, immutable, and separate. They were seen as a stage on which events played out, a backdrop against which the drama of matter and energy unfolded. Newton's conception of absolute space and absolute time dominated science for centuries. In this view, you could imagine space as an infinite container, and time as an endless ticking clock, both existing independently of whatever occupied them. But Einstein shattered that picture with a vision that was stranger, richer, and far more beautiful. Space and time are not separate. They are woven together into a single entity we call spacetime. And this fabric is not passive, it bends, twists, and curves under the influence of mass and energy. This insight changed everything about how we understand the universe. Instead of thinking of gravity as an invisible force acting across empty space, Einstein taught us to think of gravity as the curvature of spacetime itself. A massive object, like the Earth or the Sun, deforms the spacetime around it, and smaller objects move along the curves of that deformed geometry. When you see the Moon orbiting Earth, or the Earth orbiting the Sun, what you are really seeing is objects following the natural paths carved into spacetime by mass. The familiar pull of gravity is, at its core, the warping of the very fabric of reality. This idea might seem abstract, but Einstein's predictions have been tested and confirmed again and again. Light bending around the sun during an eclipse, time running more slowly near massive objects, the precise orbit of Mercury, and most recently, the detection of gravitational waves ripples in spacetime caused by colliding black holes, all confirm the extraordinary accuracy of general relativity. Yet beyond its experimental successes, Einstein's vision opened a door into questions about the ultimate beginning of space and time. If spacetime is a dynamic fabric that can bend and stretch, then it can also evolve. It can expand. And that is exactly what we observe on the largest scales. The universe itself is expanding. Einstein's equations predicted this possibility, though he at first resisted the idea, believing in a static universe. But when Edwin Hubble discovered that galaxies were receding from us, the reality of cosmic expansion became undeniable. The universe is not fixed, it is growing. Its fabric stretching in all directions, carrying galaxies apart like raisins in rising bread dough. This leads us to a profound realization. If the universe is expanding today, then in the past it must have been smaller, denser, and hotter. Following this reasoning backward, general relativity leads us to a moment when spacetime itself was compressed into an almost inconceivably small state, a singularity. At that point, our equations break down. But the implication is clear. Spacetime has a beginning. The universe as we know it emerged from a state where space and time themselves were born. Here lies one of the most radical consequences of Einstein's work. Time is not an eternal river flowing from the infinite past into the infinite future. It has a source, a point of origin. Asking what came before the Big Bang may be meaningless, because time itself began with the Big Bang. Just as it makes no sense to ask what is north of the North Pole, it may make no sense to ask what happened before time existed. This idea stretches human imagination, because our minds are wired to think in terms of cause and effect, of things happening within time. But if time itself is part of the universe, then its origin is bound up with the origin of space and matter. Einstein's vision also forces us to think differently about the concept of nothing. In Newton's view, you could imagine space as empty, a container that exists whether or not anything fills it. In Einstein's view, spacetime itself is a thing, with properties and dynamics of its own. Empty space is not nothing, it has a geometry. It can expand, contract, ripple, and warp. This means that even when you strip away all matter and energy, spacetime itself remains, shaping the possibilities of what can exist. In this sense, nothingness is never truly nothing, because the very stage of existence, the fabric of spacetime, still endures. This becomes even more intriguing when we consider quantum mechanics alongside Einstein's relativity. Quantum theory tells us that even the vacuum is filled with fluctuations, as we explored earlier. When combined with the dynamic nature of spacetime, this suggests that spacetime itself might not be fundamental, but could emerge from something deeper. Some theories in physics suggest that spacetime could arise from more basic structures, perhaps entangled networks of information or quantum fields. If that is true, then the fabric Einstein revealed to us is not the ultimate layer of reality, but a manifestation of something even more abstract. Consider also black holes, perhaps the most extreme objects predicted by general relativity. A black hole is a region where spacetime is so curved that nothing, not even light, can escape. At the center of a black hole lies a singularity, a point where density becomes infinite and our current theories fail. These singularities echo the singularity of the Big Bang. Both suggest that the fabric of spacetime has edges or boundaries where the known laws break down. In those moments, we glimpse the limits of Einstein's equations and the need for a new theory that merges quantum mechanics with gravity. Until we have such a theory, we cannot fully describe the very first moments of the universe or the ultimate fate of black holes. But what Einstein gave us was the roadmap, the understanding that spacetime is not a passive stage, but an active participant in the drama of existence. Einstein's insights also ripple into our understanding of everyday life. The fact that time runs differently in different places, depending on gravity and motion, is not just a theoretical curiosity. It is measured every day by GPS satellites, which must account for time running slightly faster in orbit than on Earth's surface. Without Einstein's relativity, your phone's navigation would be hopelessly inaccurate. This is a reminder that the bending of spacetime is not just an abstract idea, but a real and measurable feature of reality, woven into the fabric of our daily experience. In the context of cosmology, Einstein's theory is a reminder that the universe is not something floating in an empty void. The universe is spacetime itself, expanding, evolving, and carrying everything within it. When we ask whether the Big Bang came from nothing, Einstein's vision complicates the question. For if spacetime itself is a thing, then the birth of the universe was not the filling of an empty container, but the creation of the container itself. The beginning was not an event within time, but the birth of time. It was not an explosion in space, but the expansion of space. The language we use often fails us here, because our everyday concepts were never meant to grapple with such vast and alien realities. Perhaps the most awe-inspiring aspect of Einstein's legacy is that his mathematics allows us to glimpse these truths. With a handful of equations, he revealed that reality is not what it seems, that space and time are malleable, that gravity is geometry, and that the universe itself has a history rooted in the fabric of spacetime. Those equations guide our telescopes, our satellites, our understanding of galaxies, and even our speculations about the beginning of all things. They tell us that the cosmos is not fixed, but dynamic, not eternal, but evolving. not separate from us, but intimately connected to our existence. As you lie in bed, and let these ideas settle into your mind. Think of the invisible fabric that underlies everything. The pillow beneath your head, the ground beneath your home, the stars in the night sky, they all rest on the same unseen geometry. That geometry stretches, bends, and ripples across billions of light years. It began with the Big Bang, and it continues to shape the future of the universe. The fabric of spacetime is the stage, the script, and the silent actor in the play of reality. And through Einstein's vision, we begin to glimpse the depth of its mystery when cosmologists look back to the very earliest fractions of a second after the Big Bang. They encounter a mystery that stretches beyond even Einstein's theory of general relativity. While general relativity beautifully describes the expansion of space and the curvature of spacetime, it cannot on its own explain why the universe looks the way it does today. The cosmos, when viewed on the largest scales, is astonishingly uniform. Wherever astronomers point their telescopes, they see galaxies distributed evenly. And when satellites map the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang, they find it to be almost perfectly smooth, with only tiny ripples in temperature from place to place. Yet, if we imagine the early universe expanding without any special process, there should have been large differences in temperature and density. Some regions should have collapsed before galaxies could form, while others might have remained empty. Instead, what we observe is a universe balanced with exquisite precision, smooth enough to be comprehensible, but not so smooth that it lacks the seeds of structure. To explain this, physicists propose the idea of cosmic inflation, a concept as radical as it is elegant. Inflation suggests that in the earliest instant of the universe, a tiny fraction of a second after the Big Bang, space itself underwent a burst of rapid expansion, growing exponentially faster than the speed of light. This does not mean that objects moved through space faster than light, which would violate relativity, but rather that space itself expanded so quickly that distances between points grew at a staggering rate. In less than a trillionth of a second, the universe ballooned from subatomic scales to macroscopic size. This sudden stretching smoothed out irregularities, making the cosmos uniform on large scales, while also magnifying tiny quantum fluctuations into seeds for galaxies and stars. The beauty of inflation is that it explains multiple puzzles at once. One is the horizon problem. When we look at the cosmic microwave background, we see that regions on opposite sides of the sky have the same temperature, even though they are so far apart that, under ordinary expansion, they could never have exchanged information or energy. They appear too similar for coincidence. Inflation solves this by suggesting that before the rapid expansion, those regions were once close enough to interact and reach equilibrium. Then inflation stretched them apart, carrying their uniformity across the cosmos. Another problem inflation addresses is flatness. Observations show that the universe is geometrically flat, meaning that parallel lines stay parallel and the overall shape of the cosmos is not significantly curved. But achieving such flatness requires extraordinarily fine-tuned initial conditions. If inflation did not occur, even the tiniest deviation from flatness in the early universe would have magnified into dramatic curvature over billions of years. Inflation, however, naturally flattens the universe, just as the surface of a balloon appears smoother as it inflates. The rapid expansion irons out curvature, leaving behind the flat geometry we observe today. Inflation also explains why there are no relics of exotic particles predicted by some early universe theories. Without inflation, certain heavy, unstable particles might have lingered in abundance, disrupting the universe's evolution. But inflation dilutes them, stretching space so much that any exotic remnants become vanishingly rare. Thus, inflation not only makes the universe smooth and flat, but also clears away unwanted debris from the earliest instants. But perhaps the most profound consequence of inflation is its relationship with quantum mechanics. During inflation, the universe was dominated by a high-energy field, sometimes called the inflaton field. This field's energy drove the exponential expansion of space. Yet even during this dramatic growth, quantum mechanics continued to operate. Quantum fluctuations, those tiny, restless jitters of energy in empty space, were stretched by inflation to cosmic scales. The minuscule variations in energy density became magnified into real differences across regions of the universe. These fluctuations are imprinted in the cosmic microwave background as slight temperature differences, and they later grew, under the pull of gravity, into the galaxies, stars, and planets we see today. This means that everything in the universe, the great clusters of galaxies, the spiral arms of the Milky Way, the very structure that makes our existence possible, originated in microscopic quantum fluctuations magnified by inflation. The universe's grand design traces back to the uncertainty of the quantum realm, to the restless dance of fields at the smallest scales. The vastness of the cosmos is rooted in the tiniest wiggles of probability. In this sense, inflation connects the unimaginably small to the unimaginably large, binding quantum physics with cosmology in a way that reveals the deep unity of nature. Of course, inflation raises as many questions as it answers. We do not yet know exactly what the inflaton field is, or whether it corresponds to a known particle or to something entirely new. Physicists propose various models, each with different assumptions about the potential energy landscape of the inflaton. Some versions of inflation predict that the rapid expansion eventually ends everywhere, creating a single universe like ours. Others suggest that inflation may end in patches, with different regions forming separate bubble universes. If so, then our universe might be just one bubble in a vast multiverse, each with its own physical laws and constants. In this picture, inflation never fully stops. It continues eternally in some regions, spawning universes endlessly, while locally, it ends and allows galaxies and stars to form. This idea of eternal inflation is staggering to contemplate. It implies that the cosmos we observe may be just a small part of a larger, infinite reality. The laws of physics that govern our universe may be just one set among countless possibilities. And the question of why our universe exists in its particular form may be answered by saying that in the multiverse, all forms exist, and we happen to live in one that allows for life. While such ideas are speculative and currently beyond direct observation, they emerge naturally from the mathematics of inflation. Evidence for inflation, though indirect, is compelling. The patterns observed in the cosmic microwave background match the predictions of inflationary theory, particularly the distribution of fluctuations across different scales. These ripples, frozen into the afterglow of the Big Bang, are like a fingerprint of inflation. Physicists also search for more direct evidence, such as primordial gravitational waves, ripples in spacetime generated during inflation. Detecting such waves would provide a smoking gun for inflation, but so far, they remain elusive. Still, the theory has survived decades of testing, and it remains one of the strongest explanations for the universe's earliest moments. For a moment, imagine what it means that the seeds of galaxies were once smaller than atoms, that the magnificent sweep of the Milky Way, with its hundreds of billions of stars, traces its origin to quantum jitters magnified by inflation, that every star you see in the night sky, every planet, every living being, owes its existence to a process that began with randomness at the smallest scales. This vision unites the deepest laws of physics with the grandest structures of the cosmos. It suggests that the universe is not only comprehensible, but also profoundly interconnected, that the very noise of quantum mechanics gave rise to the harmony of galaxies. Inflation also deepens our sense of mystery. If the universe emerged from a quantum seed, then perhaps universes can arise again and again. If inflation is eternal, then perhaps creation itself is not a one-time event, but a perpetual process. Yet even as we consider these possibilities, we are reminded that inflation does not explain why there is something rather than nothing. It describes how the universe evolved once it began, but the ultimate origin of the inflaton field, of quantum laws themselves, remains hidden. Still, by stretching our imagination and probing the cosmos with mathematics and observation, we glimpse how the smallest fluctuations can give rise to the grandeur of existence. For those lying quietly, letting these ideas wash over them. Inflation is a story that soothes even as it astonishes. It tells us that order can emerge from uncertainty, that structure can arise from randomness, that the universe itself is the flowering of hidden potential. The galaxies overhead are not just scattered accidents. They are the magnified traces of quantum whispers, carried outward by the breath of inflation. In the first instant of time when scientists first began to imagine the earliest moments of the universe, the picture was overwhelming enough without considering anything beyond it. The Big Bang seemed to be a complete origin story, a tale of everything beginning from a single point of hot, dense energy. But as the decades passed and our understanding of cosmology deepened, the simplicity of that narrative began to stretch under the weight of new theories and evidence. Out of these explorations arose one of the most astonishing possibilities ever suggested, that our universe might not be the only one, but instead, one bubble among countless universes, each with its own laws, its own histories, its own physics. This is the essence of the multiverse hypothesis, an idea that shifts our sense of scale so profoundly that it can leave one's thoughts adrift like a small boat on an infinite sea. The multiverse is not a single theory, but rather a family of ideas arising from different corners of science. Inflationary cosmology, for example, predicts that the universe underwent a rapid exponential expansion in its earliest moments. In many versions of inflation, this expansion does not happen everywhere at once. Instead, it ends locally in patches, creating bubble universes where the energy of inflation transforms into particles and radiation, giving rise to a cosmos like ours. Meanwhile, in other regions, inflation continues, driving space to expand endlessly and spawning new universes without end. This version is called eternal inflation, and it paints a picture in which universes are constantly budding off from a cosmic inflating sea, each bubble disconnected from the others, each potentially with different properties. Quantum mechanics adds another layer of possibility. In the interpretation known as the many worlds view, every quantum decision point, every time a particle state is not definite until observed, creates branches of reality. In this sense, the universe does not collapse into a single outcome, but instead splits into multiple timelines, all equally real. If true, then every possibility exists in some universe, every choice made, every particle spin, every path history could take, realized in one branch or another. This multiverse is not spread out in space, but in probability, a staggering tree of realities unfolding endlessly. String theory, another framework of modern physics, brings its own version of the multiverse. String theory proposes that the fundamental building blocks of reality are not point particles, but tiny vibrating strings. These strings can vibrate in many ways, and the theory requires additional spatial dimensions beyond the three we experience. Different ways of compactifying those dimensions, of curling them up into hidden shapes, lead to different sets of physical laws. The result is what scientists call the string landscape, a near-infinite set of possible universes, each with different constants of nature, different strengths of forces, different particle masses. Our universe, in this view, is one solution among countless others, selected not by necessity, but by chance. For many, the multiverse is both exhilarating and unsettling. On one hand, it offers answers to some of the deepest puzzles of cosmology. Why does the universe appear so fine-tuned for life, with constants balanced delicately enough to allow stars and planets to form? If the multiverse is real, then it may be that all possible constants exist somewhere, in some universe. We live in a universe whose values happen to allow life, not because those values are uniquely determined, but because only in such a universe could observers like us arise to ask the question. This is sometimes called the anthropic principle. And while it may not feel satisfying in the traditional sense of scientific explanation, it provides a framework for understanding why the universe looks as it does. On the other hand, the multiverse raises profound challenges. If other universes exist beyond our observable horizon, how could we ever detect them? Our instruments measure light, radiation, and particles from within our own cosmos, and by definition, other universes are separated from us, inaccessible to direct observation. Without evidence, is the multiverse physics, or is it philosophy? Some argue that if a theory like inflation naturally produces multiple universes, and if inflation is supported by evidence in our own universe, then the multiverse is a logical consequence. Others caution that without testable predictions, the multiverse risks drifting beyond the boundaries of science. Still, cosmologists have explored ways that hints of other universes might leave traces. For instance, if our bubble universe once collided with another during its inflationary expansion, the scars of that collision might be imprinted faintly in the cosmic microwave background. Subtle asymmetries or circles in the sky might be the signatures of a cosmic encounter. While no definitive evidence has been found, researchers continue to search for such signs in the data from satellites like WMUP and Planck. The absence of clear evidence does not rule out the multiverse, but it reminds us of the difficulty of probing questions at the edge of knowledge. Even if we never detect other universes directly, the multiverse remains compelling for the way it reframes our place in reality. If the cosmos is truly infinite and varied, then our universe is not the center of existence, but one expression among many. This humbles us, stripping away any notion of cosmic privilege. Yet at the same time, it elevates our sense of wonder. To exist in one universe among countless possibilities is to be part of something far grander than our senses can grasp. The multiverse also raises haunting philosophical questions. If there are infinite universes, does that mean there are infinite versions of ourselves, living out every possible variation of our lives? Are there worlds where history unfolded differently, where stars burned brighter, where civilizations never rose, or where they thrived beyond imagination? In the many worlds view of quantum mechanics, this is not speculation, but a natural consequence. There is a universe where every coin flip landed the other way, where every decision led to another branch of reality. Such ideas blur the line between science and philosophy, yet they emerge from serious attempts to grapple with the mathematics of quantum theory and the implications of cosmological models. Critics sometimes suggest that invoking a multiverse is like giving up on explanation, as though multiplying realities endlessly removes the need to explain why our universe has the properties it does. But defenders counter that the multiverse is not a retreat from explanation, but an expansion of it. Just as Earth was once thought to be the center of everything, and then later revealed to be one planet among many orbiting the Sun, and then one star among many in the galaxy, so too, our universe be one cosmos among countless others. Each time, the demotion of our centrality has not diminished the beauty of existence, but enriched it. For those lying in quiet contemplation, the multiverse is more than a scientific theory, it is a meditation on possibility. It stretches the imagination outward to realms beyond sight, beyond measurement, beyond even the limits of thought. Whether or not it is ultimately true, it challenges us to loosen our grip on certainty and to embrace the vastness of what might be. The stars above remind us of infinity, but the multiverse invites us to imagine that infinity multiplied again and again, a kaleidoscope of realities branching without end. At the heart of the multiverse hypothesis lies a simple yet profound idea, that the universe may not be all there is, that what we call everything might be but a drop in a cosmic ocean, a single bubble in a sea of bubbles, each with its own time, its own space, its own story. To contemplate this is to feel the smallness of our own lives against a backdrop so immense it defies words. And yet, it is also to feel the preciousness of being here, in this universe, in this moment, aware enough to ask these questions at all. When we turn our thoughts toward the question of whether the universe came from nothing, we find ourselves standing at the crossroads of two disciplines that have been intertwined since the beginning of human thought: philosophy and physics. On the one hand, physics provides the tools of measurement, experiment, and mathematical theory, seeking to describe how the universe behaves and evolves. On the other hand, philosophy asks the questions that cannot be measured, the questions of meaning, of definition, of what it means for something to exist or not to exist. And in this grand inquiry, the word nothing takes on a weight that is far heavier than its simple sound suggests. For what is nothing? Is it an absolute void, the total absence of existence, a blank canvas without even the laws of physics written upon it? Or is nothing a concept that physics itself cannot fully embrace, since even the emptiest vacuum we can imagine still hums with energy, still contains potential? To philosophers of the ancient world, nothing was a source of paradox. The Greek philosopher Parmenides famously declared that nothing cannot exist, because to think of nothing is already to think of something, a contradiction in itself. For him, reality was unchanging, eternal, and indivisible, and the idea of nothing was an illusion born of language. Aristotle, too, argued against the possibility of a true void, preferring instead to describe change as a rearrangement of existing substances rather than the creation of something from nothing. These early thinkers wrestled with the concept long before science as we know it existed, but their struggles echo even now. For when modern cosmology tries to address whether the universe began from nothing, it finds itself using words that carry ancient shadows. In the realm of physics, nothing has never truly meant absolute absence. When physicists talk about empty space, they mean a vacuum, but a vacuum is not empty in the philosophical sense. Even in the most perfect vacuum we can create, particles flicker into existence and vanish again due to quantum fluctuations. Fields permeate the void, such as the Higgs field, which gives mass to particles, or the electromagnetic field, which allows photons to travel. The vacuum itself possesses energy called the zero-point energy, which is not zero at all. In this sense, the nothing of physics is a restless sea of potential, a stage where particles and forces already exist as possibilities, if not as certainties. This creates a tension between philosophy and physics. For the philosopher may ask, if your nothing is not truly nothing, then what is the source of your laws, your fields, your mathematics? Who or what determined that quantum mechanics would be the rules by which potential becomes reality? When cosmologists propose that the universe emerged from a quantum fluctuation, they may answer how something came from a kind of structured nothing, but the philosopher will respond that this is not nothing at all, it is something. The very existence of laws, even probabilistic ones, is already a kind of somethingness. Take, for example, the question of the Big Bang itself. If time and space began in that moment, then what does it mean to ask what was before? If there was no time, then the question of before may be meaningless. Yet human thought struggles against such boundaries. Our language and our logic are built upon the idea of sequence, of cause and effect, of something coming after something else. To imagine time itself beginning feels like standing at the edge of a cliff and looking out into a fog with no bottom. Physicists may suggest that time emerged as a property of spacetime during the Big Bang, while philosophers might ask whether this emergence itself presupposes a metatime in which the transition occurred. Here the two disciplines circle around one another, each seeking to illuminate what the other leaves in shadow. This interplay has been especially strong in the modern age, where scientists often find themselves speaking in philosophical terms, even as they try to remain rooted in empirical observation. Stephen Hawking once asked, "What breathes fire into the equations?" referring to the fact that mathematical laws can describe the structure of reality, but cannot by themselves explain why reality exists to follow those laws. The laws of physics are descriptive, not prescriptive. They tell us how the universe behaves, but not why there is a universe to behave at all. This is where philosophy presses its questions most insistently, reminding physics that beyond the how lies the deeper mystery of why. Some philosophers argue that the very question of why there is something rather than nothing may be ill-formed, a trick of language rather than a genuine puzzle. They suggest that nothing is not an alternative state of affairs, but an abstraction, and that existence is the baseline rather than the exception. Others take the opposite view, insisting that the existence of anything at all demands explanation, that the most natural state would be nothingness, and that the presence of a universe cries out for a reason. Physics, meanwhile, sometimes seeks to sidestep the philosophical tension by showing how universes can spontaneously arise from quantum laws, as in models of vacuum fluctuations or quantum tunneling. Yet in doing so, physics assumes the prior reality of quantum laws, which is itself a kind of existence that demands explanation. The dialogue between philosophy and physics over nothingness is also shaped by human imagination. When we contemplate nothing, we often picture a black void, an empty space, perhaps silence and darkness. But this is already something, already space, already time. True nothingness, if it could be conceived, would have no dimensions, no duration, no possibility. It is not a vacuum, but the absence of even the concept of vacuum. It is the absence of absence. And here, the mind falters, because thought itself is structured upon contrasts, upon something to compare against something else. To imagine nothing is to imagine, paradoxically, something. And so, the question of whether the Big Bang came from nothing is not merely a matter of physics, but also a mirror reflecting the limits of human thought. In practice, physicists often find it more productive to redefine the question. Instead of asking whether the universe came from nothing, they ask how the universe as we know it could emerge from states with minimal structure, states that resemble nothing as closely as possible while still being describable. They investigate the mathematical properties of vacua, the behavior of quantum fields, the dynamics of spacetime near the Planck scale. Philosophy, in turn, reminds them that redefining nothing as almost nothing does not erase the deeper mystery. Each refinement of the scientific model makes the question sharper, but it never fully erases it. Theologians and metaphysicians sometimes enter the discussion as well, proposing that nothingness is not the true origin, but that being itself requires a ground, a necessary reality, beyond contingency. Some argue for a first cause, an uncaused cause that stands outside the chain of events. Others argue for a purely naturalistic account, where the universe or multiverse is self-contained, requiring no external explanation. The dialogue among physics, philosophy, and theology can become contentious, but it also illustrates how deeply the question of nothingness cuts across human thought. It is not merely an academic puzzle, but one of the most fundamental mysteries of existence, for the person lying in bed at night, listening quietly as these ideas unfold. The meeting of philosophy and physics offers not answers, but reflections. It reminds us that the universe is not only a set of equations and measurements, but also a source of wonder, a mystery that cannot be dissolved entirely into numbers. To hear that the universe may have sprung from a quantum fluctuation is awe-inspiring, but to realize that this still leaves the question of why there are quantum laws at all is humbling. To hear that nothing in physics is filled with restless energy is fascinating, but to realize that our very concept of nothingness slips through our grasp whenever we try to hold it is deeply moving. It tells us that we are creatures caught between knowledge and mystery, capable of great insight, but also destined to encounter limits. And yet, in encountering those limits, we are reminded of the immensity of the cosmos and the strangeness of existence itself when we step back and reflect on the journey through cosmology, philosophy, and physics. One question lingers in the quiet space between thoughts. Why does any of this matter? Why spend so much time asking whether the Big Bang came from nothing, or whether there are multiple universes, or whether quantum fields are eternal? The answer lies in the profound human desire to understand not just how things work, but why they exist at all. The wonder of existence is not simply an abstract curiosity, it is a force that shapes the way we see ourselves, our place in the universe, and even the meaning of our lives. And so we return to the heart of the matter. Why does this question matter? Because it awakens us to the miracle of being. Because it connects the smallest flicker of consciousness to the largest sweep of the cosmos. Because it reminds us that the universe is not simply a backdrop for our lives, but the very substance of them. The stars, the galaxies, the laws of physics, the vastness of space and time, all of it is part of the same existence that allows us to wonder, to dream, to reflect. And in that realization lies a quiet peace. The kind that comes when we understand that even in the face of mystery, we are at home in the universe as we have traveled through these keynotes together. From the first fiery instance of the Big Bang to the quiet mysteries of philosophy, we find ourselves in a place of both knowledge and humility. Science has carried us far, revealing that the universe expanded from a hot, dense beginning, that quantum fluctuations may have seeded galaxies, that inflation smoothed the cosmos, and that perhaps countless universes stretch beyond our reach. Philosophy has reminded us that even as physics redefines nothing into structured vacuums and quantum seas, the deeper question of why there is something rather than nothing remains unresolved. The Big Bang may have sprung from quantum fields, from an eternal, inflating multiverse, or from laws as yet unknown. Or perhaps, as some philosophers suggest, the question itself points beyond what the human mind can fully comprehend. What we can say with certainty that we live in a universe that is vast, ordered, and filled with mystery, one that has allowed life and consciousness to emerge, and with it, the ability to reflect on origins at all. The wonder of existence is not diminished by the absence of final answers, it is amplified by them. The universe may have come from nothing, or from something deeper than nothing we cannot yet define, but the fact remains, there is a universe. There is life, and there is awareness. To rest in that truth is to rest in awe. And in the quiet of night, as we allow these reflections to settle, we are reminded that the greatest gift of existence is not only being here, but being able to wonder at all.